Pleasure to have today Bill Minicozzi from MIT, and he's going to speak about mean curvature flow and high codimension.
Thank you. Thanks. Nice to see everyone, or sort of see everyone. So a couple things before I start. So first of all, everything I talk about is joint work with Toby Colding. Second, my hope is that I'll never go more than at most 5 to 7 minutes being the only one talking. So questions are very much encouraged. I have a natural tendency to want to try to get through everything on my slides. That's impossible. If I were to do it, I would feel maybe some sense of achievement at the end, but the whole thing would have been absolutely useless because, by a few minutes through, nobody would really be getting anything. So please ask questions and let's make this as interactive as possible. Okay, so I'm going to talk about some results about mean curvature flow in higher codimension. So mean curvature flow is best understood in codimension 1. There are a number of reasons for that. One analogy that you can imagine is if you just think about minimal submanifolds. So the minimal varieties, say, are the stationary case or time-independent case of mean curvature flow. In codimension 1, the theory is substantially simpler than it is in higher codimension. There's some really interesting things that can start to happen once you get that additional codimension. It happens for a number of reasons. It happens for reasons related to the maximum principle. It also happens because there's a much more interesting structure for the second fundamental form, which becomes vector valued instead of scalar valued. So this shows up in a number of ways. One of those ways is in understanding Simon's equation. So this is the elliptic equation that the second fundamental form satisfies. So the sort of the pure second order part of that is very similar, but there are lower order parts, operators that Simon's discovered in his work in the late 60s that can be pretty complicated and allow some interesting new phenomena to occur. So for that reason, we're going to take in many of the things that we do, we'll take a slightly less geometric approach, and we're going to work more with function theory. So that'll become clear as we go on. Some of the ideas that are involved that are function theoretic actually came out of things that Toby and I did for manifolds with non-negative Ricci curvature and harmonic functions a very long time ago at this point. Okay, so one of the so there are going to be two strains of results about mean curvature flow, and the first is that you're going to start with some flow. A priori, it might lie in a huge Euclidean a space of huge Euclidean dimension. But we'll see that in many cases, you can say it actually lies in a subspace of much lower dimension. So that I'll explain what this means, but basically it means that a lot of these variables are extraneous. And if you were to rotate it, you could get it down so something was really happening in a much lower dimensional space and get rid of those extra variables. And so we'll see one particular application. So, cases where this can be applied. One of them is in terms of understanding generic singularities or singularities that are stable under perturbation. And so that strain of results, the bounds that we'll get, there'll be some fixed bound for the codimension of the submanifold, but it won't necessarily be all that sharp. We'll see a second strain of results where we can actually get extremely sharp codimension bounds. And so in this case, or in certain cases, we'll say that actually it was really just a submanifold evolving in codimension 1. Okay, so that's as sharp as you can get. And so this will apply in some important cases. So in particular, it will apply to cases where there's some cylindrical structure. So the cylindrical structure is a natural one for reasons that I'll explain. One of them, if you come from the point of view of GMT, is that these are the ones with the space of the greatest space of translation and variance. So this means this is the top strata of the singular set when you do a stratification. So this really applies to most singularities from that point of view. Okay, and a second result that I'll touch on but won't be able to say too much about is I'll prove a rigidity theorem for cylinders in any dimension in codimension, which shows that if you have one of these cylindrical singularities, and it's close, cylindrical now, meaning just on a fixed large compact set, then in fact it's identically equal to a cylinder. Okay, so now we'll back up and I'll just explain some of the basics of mean curvature flow. When I talk about mean curvature flow and we try to get an intuition, everything I'm going to show you is codimension 1, because then I can draw the pictures. Okay, so what this is, a mean curvature flow is a family of evolving submanifolds. You know, in principle, one can look at weak solutions and do things like that, but when you're trying to think about, get an idea, that you would just imagine smoothly evolving smooth submanifolds. And so they're indexed by this index T, so M of T is a family. And each point on a hypersurface is going to move in its normal direction with speed equal to the mean curvature. So I've drawn it here as though it's the bold H's, this is the mean curvature vector. My pen doesn't want to do anything. Okay, well, so much for that. And this is an example of a geometric heat equation. So this is best understood in codimension 1, as I mentioned, and really best understood for convex subsets in codimension 1. So here I've drawn a case of curves. So in this case, if you start with a closed convex submanifold, then it's going to remain that way. So it stays closed, it stays convex. If it was initially embedded, so it didn't intersect itself, it will stay that way. It will contract inwards, and then it'll, after some finite amount of time, it will just disappear. Okay, when it disappears, we call that an extinction singularity. And so here, what you see, the outermost curve, the darkest curve, is the initial curve. And then as it gets lighter, the curves keep moving inwards. If you look at the one, the last one that you see it almost looks round. It almost looks like a circle. And so that is exactly what happens. In the case of curves, this was shown by Gage and Hamilton. And in higher dimensions, it was shown by Gerhard-Huisken. So one thing that's interesting, and here when we say it looks more and more like a circle, well, it's disappearing, it's becoming convex. What I mean is if you take a time just before it disappears, the curve's now extremely small. If I magnify it back up to contain area pi, then it's gonna be very close to a circle. If I go even closer in time to the extinction and magnify that up, that's even closer to a circle. So that's the sense in which it's asymptotically circular. And in higher dimensions, asymptotically spherical. One thing that's curious about this is that Gage and Hamilton's proof worked only for curves, and Huisken's proof worked only in dimension 2 and higher. And the reason was that they focused on different aspects of being round. So Gage and Hamilton showed that the curves that you got were improving their isoperimetric ratio until it was nearly optimal, and then asymptotically optimal. And so that means it has to be the circle. What Huisken showed is that the second fundamental form, was becoming umbilic. So what that means is this second fundamental form has all these different eigenvalues, which we call the principal curvatures. And because it's convex, each of these is positive. But what's happening over time is the difference between the largest and the smallest is getting smaller. And this, and I mean, even after you say divide by the average of them or something. Okay, so what that meant is the asymptotic shape you were getting has all of its principal curvatures the same. Such a thing is said to be a totally umbilic. And in Euclidean space, the only thing that you can have that has that property is a circle, is a sphere. That forces it to be round. Of course, there's a trivial case. If that eigenvalue was all 0, then it wouldn't be round, it would be flat. But those are the possibilities. Okay. So now once you leave the convex world, things get more complicated. So I've drawn here a picture of a snapshot in time of a surface. This is called a marriage ring. It's a thin torus of revolution. And if you make it thin enough, it's mean convex. What mean convex means is the mean curvature has a sign, right? So this is a surface, so there are two principal curvatures. And it's obviously not convex, so they aren't both positive. However, the sum of them is positive, which means it's mean convex. And so this means the flow is going to push it inwards. So in the applied math literature, they would call this a monotone flow. Okay, it's always moving inwards. So this one has a symmetry of revolution that will be preserved under the flow. And so what happens is the only way it can, and it's going to shrink down, the only way it can disappear is along a set which has the same symmetry. And so that has to be a circle of revolution. So what happens is this disappears, the flow is smooth until it becomes extinct along a round, a round circle. Now, if you were to zoom in on the singularities that are happening here and rescale it back up to unit size in some sense, you would see that instead of becoming round, instead of becoming spherical, they were becoming cylindrical. Okay, so this set where it disappears is called the singular set. Okay, so there's a rescaling analysis or blow-up analysis that we use to try to understand singularities. So if you are into minimal submanifolds, which many people are, myself included, then you've thought about the blow-up analysis there. If you have a singularity of a minimal variety, then if you zoom in on it and magnify it back up, and keep doing that further and further magnifications, it converges to a minimal cone. And so this cone structure, right? So this reduces the complexity by one dimension, because all of the information is then contained in its intersection with the sphere. So this link of the cone, and this link is minimal in the sphere. And so we've now, it's like an inductive argument. In order to understand the possible cones that occur, we now need to understand minimal submanifolds of something one dimension less. And so you see how you can build a theory that way. Okay, so there's a similar rescaling analysis that goes on in these parabolic problems. So now the flow, you have the surfaces evolving over time. So we need to rescale in both space and time. So a similar thing is done in Ricci flow. And in that case, I heard Hamilton once describe it as, you think of the Ricci flow as a movie. And so what you do is you zoom in, right? You magnify the picture, and at the same time you run it in slow motion. Okay, and so if you adjust these factors in the appropriate way, what you get is still a mean curvature flow, or in the other case, a Ricci flow, which is now zooming in on where the action is, where the singularity occurs. And in the limit, you get this is called blowing up. You get the flow, which now, because you slow down infinitely much, the flow extends all the way back to minus infinity. The flow now exists for an infinite amount of time. Okay, so just like if you blow up a singularity of a minimal submanifold, you now get a complete minimal surface. If you blow up at a singularity of a mean curvature flow, you get what's called an ancient mean curvature flow. It's defined all the way out to time minus infinity. So if you want to understand what these singularities look like, or what the flows look like near a singularity, what you want to understand are these ancient solutions. Okay, they model the behavior of flows at and near singularities. There's one very special type. So just like we had cones for the blow-up process of minimal varieties, the ones that are now dilation invariant under this blowing up process are called self-shrinkers, or self-shrinking solitons for the flow. And I'll just call them shrinkers.
Sorry, Bill. So when you say that's a shrinker, it's because that's where you're using the Huisken monotonicity formula to say that?
Yeah. So exactly. Yes, you get an ancient solution regardless.
Regardless, right? But I mean, the monotonicity formula is what is giving you this shrinker.
Exactly. And that's right. And so there's a monoton, and just like for the minimal case, there's a monotonicity formula. This way, it's a formula of Gerhardt-Huisken. And when you have this monotone quantity, which only has a finite amount of oscillation. So in the limit, when you blow it up, that monotone quantity is constant. Constancy there implies that it's invariant under dilations. In this case, it's parabolic dilations, which dilate both space and time. And so these self-similar things are called shrinkers.
Uh-huh.
Yep. Thank you, Camilla. And so in that case, so just like...
Just sorry if I'm interrupting too, but they're not all shrinking, right? I mean, like the idea is that they're a little bit like the sphere going to a point, but there are also guys which are not actually doing that, right?
So yeah, so here, yeah, excellent question. Okay, so what it means when it's shrinking, it means if I take okay, so let's think about it like a cone would be. So now the analog of a link is to intersect with a time slice.
Mm-hmm.
So if you intersect, we usually intersect with a time slice at time -1. And so what you get at a future time is at a time closer to 0 is just the time -1 thing scaled down by the appropriate amount. So in that sense, they are all shrinking. But if the time -1 slice is non-compact, then it may not shrink away to nothing. So for instance, the time -1 slice might be an infinite cylinder of radius 1/√2. And so then the radius of the cylinder shrinks as you go down to the origin. But of course, that line still goes off to infinity in both directions. So that's one new feature, is that now our singularities can be non-compact. If you have the minimal submanifolds of the sphere, they're always closed. And so, but now we have these singularities that even though they're shrinking, they may still be infinitely large at every time. Right, and so in fact, the Huysken's monotonicity is only a backwards monotonicity. So when I say these flows are ancient, they're only defined backwards to time -infinity. They are not a priori defined past time 0, past the time of the singularity. If you were to try to do a rescaling to the future, instead of getting a shrinker, you would get something called an expander. The problem is that in very few cases can people show that it actually converges to an expander. There is a monotone quantity, but the problem is it's always infinite. So it makes it a little tricky to get your hands on it. There are certain cases, if something is asymptotic to a cone, then people are able to do some kind of regularization process where you can subtract some other infinite quantity from it and show that the difference is still monotone and get, right. So, but there is this difference now between backwards and forwards in time. And I'd like to pause to, Camille, thank you for the questions. The more, the better. Okay, so this is what we have to do. And so again, these are the shrinkers. It was Gerhardt's monotonicity. He was initially interested in a setting which is called the type 1 blowup. And what that is, that's when you assume kind of some scale invariant blowup rate as you approach the singularity. And so then the rescalings actually converge smoothly. If you don't have this type 1 blowup, then you won't get a smooth limit necessarily as you do it. You get a limit in a geometric measure theory sense. Okay, so as varifolds. And so Tom Illman and Brian White observed that you could use methods from GMT and Gerhardt's formula and get one of these tangent flows in every case, but it just might not be smooth. Although Tom showed that in dimension 3, it always was smooth. The convergence wasn't necessarily smooth, but the limit thing was smooth, right? The reason the convergence might not be smooth was because of multiplicity of convergence. Okay, so you can't use something like Brachy. In the minimal case, it would be Allard to converge smoothness of convergence. Okay, so now this time -1 slice, which is the analog of the link for a cone, this does not satisfy an elliptic equation. This doesn't satisfy a parabolic equation. This one actually satisfies an elliptic equation, which we call the shrinker equation. And so that's that the mean curvature is equal to the normal part of the position vector divided by 2. In codimension 1, this position vector normal part divided, is usually called the support function, especially for people that work in convex geometry. And so this looks a lot like the minimal surface equation. So the normal part of the position vector, that depends on the 0th and first derivatives, okay, but not second derivatives. So from the point of view of what type of PDE, a principal symbol, anything like that, this is just like the minimal surface equation, but it has different first and 0th order terms in it. Okay, so now I hope that I've at least made it plausible to you that if you want to understand singularities in mean curvature flow, there are 2 things you really want to understand to start with. One is you really want to understand what shrinkers can occur. Okay, so what are the shrinkers and what are their properties? The second thing that you'd like to understand more generally is what can you say about ancient flows? So if you blow up at a fixed point, so if you do your tangent flow where the point you're blowing up is always fixed, you're guaranteed to get a shrinker. if you want to understand finer properties of the singularity and the behavior near the singularity, sometimes instead of fixing the point, you take a sequence of points converging to the singularity and do blowups around that. In that case, the monotonicity does not give you that you have the self-shrinking structure, but you do still get an ancient solution. Okay, so for many finer properties, it's important to understand all ancient solutions, or at least classes of ancient solutions. For the first properties, we just want to understand shrinkers. So that's our motivation and our setup. Okay, so I'd like to start by explaining or just listing a few examples of shrinkers and saying which ones are important and why. Okay, so the ones that would be the most important for this talk are round cylinders. So we already met spheres, but you can get, so you can get a sphere in any dimension. But if you take one of these spheres and just cross it with the Euclidean factor, it will also satisfy the shrinker equation. Okay, and so these are called round cylinders. The radius of the sphere is determined. If you look at this h as x perp over 2, this fixes a preferred radius, and so that's why the radius of the sphere of dimension k is square root of 2k. If you think about it, these things, the mean curvature flow is supposed to shrink these uniformly. Well, the rate at which it is shrinking is going to depend on the dimension, right? Because that's how many eigenvalues that you add together to get the mean curvature. So the larger the dimension of the sphere, if it was the same radius, the faster it would be shrinking. And so that's why the two play off each other. Okay, so as I already mentioned, these cylinders are in one sense, the most important singularities, and that's because of dimension reducing. So if you have any if the dimension of the Euclidean factor, that tells you in terms of the stratification, the dimension of which part of the stratification of the singular set. So the larger the Euclidean factor, the more prevalent these singularities are. The biggest, so if you had an Rn minus 1, and you're embedded, this forces you to be an S1. Okay, maybe I could say more there, but it would probably make it less clear. So
I have a very naive question. So do you already know that your singularities have some kind of symmetry?
You don't. No, not. And in fact, most of them do not have symmetry.
That's what I would guess. They
right.
would not. They could have kind of crazy structure, perhaps.
Exactly. But what happens is singularities with no symmetry, those tend to be isolated singularities. And so if you think about the larger singular set, so right now, so we have this flow that is smooth we hope most places, and then there are these sets where it becomes singular, that the set where it's singular is automatically closed, and we'd like to show it's as small as possible. So one way to show it's small is to say its dimension is small. So the analogy to think of here is if you look at area minimizing hypersurfaces and you say in a Riemannian manifold, then the singularities are codimension 7. So up until dimension 7, you don't even see them at all. And then after that, they're really, really tiny. In mean curvature flow, so there's a similar theory in mean curvature flow, which is not nearly as well developed, except in the case of mean convex flows. And so if the singularity that you get, okay, so then I should say, there's this theory of Almgren-Federer dimension reducing. And so what it says is if you look at this singular set and you stratify it, and the way you stratify it is you're going to say, the top stratum of the singular set, these are the points where the blow up that I get there has translation invariance of maximal dimension. It turns out that each of these strata has dimension, say in a covering sense, bounded by the translation invariance, the number of degrees of translation invariance. So this tells you the ones that you really need to, if you just want to say a statement about, say, the dimension of the singular set, what you need to do is understand the singularities that do have symmetries that have these translation invariances. Does that make sense? Yeah, it's an amazing insight. It's really powerful use of geometric measure theory to prove something like that.
Thank you.
Thank you. Okay, so these, and then Brian White did a parabolic version of this. The Almgren-Federer was done in the elliptic case, and Brian observed a parabolic version of this dimension reducing. And so that's why these are the ones that we're most interested in understanding. So in codimension 1, there are 3 other reasons why you might be most interested in cylinders. The first is they're the only mean convex singularities in codimension 1. So Gerhard originally showed that in 2 papers in 90 and 93, assuming a bound on the principal curvatures. Toby and I removed the bound on the principal curvatures and showed that even if the curvature was becoming arbitrarily large, or even with certain singularities, it would still force to be mean convex. The second is, in codimension 1, Toby and I showed that these were the singularities that could not be perturbed away. And the third reason is that in R3, Brendel showed a couple of years ago that these were the only genus 0 singularities. So topological genus 0. Brian White showed a while back that the genus was monotone under the flow. So even if a mean curvature flow of surfaces went through singularities, the genus at a later time was not larger than at the initial time. Okay, so that's why it's reasonable to track the genus in terms of singularities. Okay, there's a second large class of examples of shrinkers, and this only occurs in higher codimension. And this is if you have any minimal submanifold in a sphere, it gives you a shrinker. And the idea here is that the sphere itself, if it was moving by mean curvature, it would shrink self-similarly. If you have something that's minimal in there, its mean curvature vector is equal to that of the sphere. That's what makes it minimal. And so it just goes along for the ride. Okay, so now this gives a huge class of examples. There are many families of this constructed by Calabi, DeCarmo Wallach, and many others. Okay, it also means that everything that I prove about a shrinker automatically applies to minimal submanifolds of a sphere. Okay, so now the way that we're going to get a handle on these guys is we're going to look at the coordinate functions. So if you work in complex geometry, this would perhaps remind you a little bit about things like the Kodaira embedding theorem. So how do you understand a complex variety? You think of you construct holomorphic sections of line bundles. So how are we going to understand a minimal minimal submanifold? You might find harmonic functions. A mean curvature flow, you find solutions of the heat equation. Okay, so the coordinate functions on a mean curvature flow actually satisfy the heat equation. Okay, so one of the things that makes this difficult is that, of course, it's a heat equation on a family of evolving metrics. So the Laplace operators keep changing. So in particular, the t derivative and the Laplacian do not commute. And this creates a lot of troubles in terms of understanding this analytically. Okay, I want to introduce another friend that we're going to meet up with. And this is the drift Laplacian or Ornstein-Uhlenbeck operator. And so on Euclidean space, I'll always write this as script L. The second order part of this is just the Laplacian. But then there's this first order part where I take the gradient of the function and I interproduct it with the position vector. And then there's a normalizing factor, a half. This is the operator that is self-adjoint for this Gaussian inner product. So if I use a weighted L2 inner product where I weight by the Gaussian, and in fact, the coordinate functions with respect to this operator are eigenfunctions with eigenvalue a half. Okay, so, right. So by the way, if you looked at the eigenfunctions of this operator in general, let's say on the line, so just on R, these have a name. They're the Hermite polynomials. Okay, and so they show up at the half integers, the integers and half integers. That's where the eigenvalues are. And in fact, the degree of the polynomial is twice the eigenvalue. So so the coordinate functions are degree 1 with eigenvalue a half. Okay, this drift Laplacian on Rn can be thought of as a special case as a drift Laplacian on a shrinker, a mean curvature flow shrinker. So what I'm going to do here, the script L operator looks extremely similar, except instead of having x, I have the tangential part of x. So this is, I take the gradient of the function and interproduct with the tangential projection of x. If my shrinker was a minimal submanifold of the sphere, then the position vector on a sphere is actually normal to the sphere. So this second term the first order term goes away, and it just becomes a Laplacian. Okay, so this interpolates between those two operators. And now, again, the shrinker equation tells me that the eigenfunctions, the coordinate functions are, again, eigenfunctions for the drift Laplacian on any shrinker. On a minimal submanifold of the sphere, this says the coordinate functions are Laplace eigenfunctions. Okay, but for any shrinker, I get this with the drift equation. Okay, so now I want to sketch out an idea of how you might use something like this to get some control on the codimension. And I'll do it in a case where we can get really, really strong control. So if I have a shrinking curve, so this is a curve that satisfies this shrinker equation. And it's in Rn, where R capital N, where N is a large thing. So it's a curve in some huge dimensional space. Then each coordinate function restricted to the curve satisfies this ODE, which just says the script L operator. It's a half eigenvalue for the script L operator. So the thing is, it's the same ODE for every coordinate function. It's a second order linear ODE. So this means there are only two linearly independent solutions to this ODE. Once I specify the value in the initial condition, that determines the solution. Okay, so I have a two-dimensional family of linearly independent solutions, and on the other hand, all of the coordinate functions satisfy it. That means essentially there are only two of these coordinate functions that are linearly independent. So that means that there's some two-dimensional plane that the shrinking curve is contained in. So this shrinking curve that a priori was in this huge dimensional Euclidean space, I can rotate the space so it's just in a plane, the ordinary plane. And then all these other coordinates are actually extraneous, nothing's happening. Okay, so now this is convenient because in the 80s, Abrich and Langer classified all of the solutions in the plane. They basically look like, a first-year calculus student's nightmares. All of these things that you draw for using polar coordinates, cardioids and lemniscates, all of these things, they're locally convex. They keep looping around, and eventually they close up. So that's what the solutions look like. There's only one of them that doesn't intersect itself, and that's the circle. And then there's the limiting infinite trivial solution of a straight line. Those are the Abrich-Langer solutions, and those are the solutions in all things. So this tells us that if I was to have a curve shortening flow in some huge Euclidean space, and I do the blow up at a point to find the singularity there, it's just on this list of curves in the plane that Abrich and Langer classified. Okay, so and notice that so this is a nice application of using this ODE for the coordinate functions to really tell us something about the flows. We'd like to do that in general. Of course, in general, the coordinate functions are not going to satisfy an ODE, they'll satisfy a PDE. So I can't just use ODE theory to bound the number of solutions. Okay, so, but now hopefully I've motivated the problem. We'd like to understand, how do I control the number or the dimension of the space of solutions to this sort of equation? All right, so now we're going to segue. We're going to change topics a little bit. I want to talk about some classical results in geometry and analysis. So remind you of the Liouville theorem. So if you have a bounded harmonic function, or in fact even just a positive harmonic function that's defined on all of Rn, it has to be constant. In the early 70s, Yau generalized this to manifolds with non-negative Ricci curvature. Of course, this can't be true on all manifolds. If you had hyperbolic, like the hyperbolic disk that has constant curvature -1, but of course any boundary values you want, say any continuous boundary values you want, you can find a harmonic function with those asymptotic values. Okay, so that you need some geometric condition, and non-negative Ricci curvature is a natural one that works. Okay, so we'd like to go a little further. So instead of just saying they're constants, if they're bounded, I'd like to ask, suppose I allow the function to grow a little. Then what can you say? Okay, so what I'm going to do is I'm going to define a space HD, and this will be the harmonic functions which grow polynomially of degree at most d. So the Laplacian is 0, and the sup norm on a ball of radius r is bounded by a constant times r to the d. And so this constant has to be the same for every ball, but it's allowed to depend on the function u. Okay, so if it does this, it grows of degree at most d. And this is the space of harmonic guys that do this. That's the space hd of n. On Euclidean space, hd of Rn just consists of harmonic polynomials of degree d. I mean, obviously, any harmonic polynomial of degree d sits inside hd of Rn. And the fact that those are all of them, you can prove that just using elliptic estimates. So, all right, so Yau conjectured that there was a stronger Liouville property. So he conjectured just like manifold, so he had shown that manifolds of non-negative Ricci curvature from the point of view of the Liouville theorem were just like Rn. And he conjectured, well, maybe they're also just like Rn in terms of the these generalized Liouville property, or functions of slow polynomial growth or polynomial growth. So of course you don't have polynomials on a general manifold, so he's not going to conjecture what the functions are, but he did conjecture that the space of them is finite dimensional. And again, obviously you need something for this to be true. On hyperbolic space, this would fail miserably even without allowing any growth. Okay, so and then really at this point, very long time ago, Toby and I showed that this conjecture was true. And in fact, the dimension for the space HD was always bounded by a constant times d to the n minus 1. And so this is up to the point of the constant. This is the same thing that you get on Euclidean space. Okay. In fact, we actually proved something stronger than that, more general than that. We showed you didn't need non-negative Ricci curvature. You could make do with with two properties that are true for non-negative Ricci curvature, but are much more flexible. So the two properties are a volume doubling bound. So this means that if you take a ball of twice the radius, its volume is bounded by a fixed constant times the original ball. Okay, that's called volume doubling. Of course, on Euclidean space, if you double the radius, the volume just goes up by 2 to the n. Okay, but if you have a manifold with a volume doubling, it goes up by at most a fixed constant every time you double. And the second thing you needed was a Poincare inequality. So you wanted a Neumann-Poincare inequality on every ball. Okay, so both of these properties hold for non-negative Ricci curvature. The thing that I really like about these properties are two things. The first is to define these properties, you need less regularity. Okay, so to define curvature, you need a fair bit of regularity. Say it depends, say, on second derivatives of the metric, whereas these things can make do with much less. The second thing is that these properties are flexible. So if you take your manifold and you make any bi-Lipschitz change of metric, so change the metric by its bounded factor above and below, it still has these properties with different constants, but it still has both properties. Both of these properties are stable under that change. So that means, as a corollary, we immediately get that any manifold that's bi-Lipschitz to a manifold with non-negative Ricci curvature, then the harmonic functions of polynomial growth are finite dimensional. That was not even known on Euclidean space. So it was not known if you had a bi-Lipschitz metric on Rn that was bi-Lipschitz to the Euclidean metric, whether or not these spaces were finite dimensional. The strongest that was known there was a theorem of Moser and Struve. They proved that was true if you also assumed that it was periodic. So if the metric came from the universal cover of a metric on a torus. Okay. And I should say that there are a lot of people who proved great results along this line. I'll just flash that there, and maybe keep moving. I should say you should be very worried. None of the screens that I'm looking at show a clock. I should better rectify that. Okay. And in fact, the flexibility of these properties is really useful and allows it to be applied in a bunch of different settings. So for instance, it applies to discrete problems. You can make all of this, make sense of these ingredients, these things of volume doubling and a Neumann-Poincare for operators on graphs, for instance. Okay, you can also then apply it to some of these problems from geometric group theory. And Bruce Kleiner did that to give a new proof of Bromov's classification of groups of polynomial growth. Shalom and Terry Tao built on what Bruce did to prove a finitary version of that, basically. So yeah, an effective version. You don't have to go all the way to infinity. Okay, so that's our quick review of the spaces HD and harmonic functions of polynomial growth. And so how does that fit into our parabolic world right now? So I'd like to define some parabolic version of these spaces and prove something similar and then relate it to the flows. The right notion is this space that we call PD. And so these are solutions of the heat equation, which are ancient. So they're defined all the way back to time minus infinity. And if you look in space-time balls, they grow polynomially. So as you move backwards in time and out in space, the soup norms are bounded by a polynomial. Okay, and so this is a space PD. You need some, for the heat equation is extremely flexible. If you take basically, or virtually arbitrarily awful initial data for the heat equation, it just blows up less than double exponentially, right? Then you can define a solution that will move 1 unit forward in time, and certainly, you can have almost any properties that you want. You're not going to show any finite dimensionality this way. Okay, the space of these things is going to be horrible. The right thing turns out to be being ancient. The philosophy here is that the heat equation is smoothing. Okay, so if you run it, the longer you run it, the more it smooths. If you run it infinitely long, it smooths infinitely. So if you want some kind of rigidity, like a Liouville theorem, you're going to want to run the heat equation all the way back to minus infinity. Okay, so this is the philosophy. These are the spaces PD. On Rn, again, it's easy to see that the only things that satisfy this property are actually polynomials, caloric polynomials. So they're polynomials in both T and the Euclidean variables. And the dimension of PD is d to the n here on Rn. Okay, so I better pause because I'm at risk of losing people. Camilo, is that pretty clear, the dimension of the definition of PD?
Absolutely.
Yeah. Okay, good. All right, so, right, and so the first thing that we did here is we showed that these spaces are bounded. Notice that, of course, this space PD, this includes all harmonic functions of polynomial growth. Okay, because those would be static, time-independent solutions. Okay, so the first thing we did is we showed that these spaces were finite dimensional. And in fact, we did this first on manifolds where the Laplacian didn't change. Okay, so time-independent metrics. And in this case, we showed that the dimension of P was bounded just in terms of the dimension of H. And this bound, this turns out to be sharp, and of the sharp order. And it gives that for manifolds of non-negative Ritchie curvature, you get a bound of d to the n. And this exponent is sharp. Okay, so if the harmonic ones were a constant times d to the n minus 1, if we go ancient caloric, you get all the way up to d to the n. Okay, so shortly before we proved this, Fenghua Lin and Q.S. Zhang, they adapted the way that we argued back in the old harmonic case to prove the bound d to the n plus 1. Okay, and this bound d to the n plus 1 is what I would have guessed was the optimal bound. So by analogy, in these parabolic problems, you treat time as if it has dimension 2 because of the way it scales relative to space. And so in the harmonic case, we showed that the dimension of HD was the dimension of the space minus 1, the exponent for the dimension of HD. So here I was expecting n plus 2 as the dimension of Rn cross time minus 1. And so that would give me a d to the n plus 1. And that's what our methods were well set up to do. And that's what they showed. So we were surprised when we were able to sharpen it and show it was actually one, the exponent was 1 less, the sharp exponent. There was something really parabolic going on. Okay, so how does this relate to, why is this relevant to mean curvature flow? So on a mean curvature flow, the coordinate functions, they satisfy the heat equation, and they certainly grow linearly. So those are in the space P1 on a mean curvature flow. So if I could get a bound for the dimension of P1, I would get a bound for the number of linearly independent coordinate functions, which is to say a bound for the codimension that the space actually, that the flow actually lives in. Okay, so that's the philosophy. Just like that toy problem that we did for shrinking curves, where we used the ODE to bound the number of linearly independent coordinate functions. Now I want to use these kind of arguments to try and get that bound. One difficulty, of course, the result that I just told you about does not apply, because we did that for time-independent metrics, and a crucial step in the proof was that the t derivative and the Laplacian commuted. Without that, that proof falls apart. Okay, so we need to do something different. Okay, so now I'd like to introduce you to some of the other objects that play a role in this work. So the first is this, what we call the Gaussian area. So here, if I have some submanifold, or even more generally a varifold, or measure theoretic object, sigma, then I define its Gaussian area to be the integral of the Gaussian over. And I so e to the x minus x squared over 4. And I put this factor of 4 pi to the minus n over 2 in front. And this is just chosen so that if I take a plane through the origin, then this Gaussian area is 1.
So why does the Gaussian play a role here in these questions?
Yeah, so right, so there's several, yeah, that's a great question. There's several different reasons. Okay, so one thing is the Gaussian, we saw that the Gaussian weight was exactly the right weight where the drift, where the script L operator arose, right? And the shrinkers that are the singularities for or self-similar things for mean curvature flow, the natural operator on them is exactly the script L operator. So there's some link which comes in through that, which really has to do with scaling. So right, so there's that. So this is the functional for which the shrinkers are critical points. So somehow there's this link there, which makes it work. The second thing is Huysken's monotonicity is for the integral of Gaussians on the flow. And it's exactly that quantity. And so what it has to do with is that if you look at the Gaussian and you apply the heat operator to it on an evolving minimal submanifold, then you get some inequality versus what you would expect in Euclidean space.
Okay, thanks. Yeah.
Okay, so we take this Gaussian area here, and so we just, this gives us a functional. And then we're going to define an entropy. And the entropy is, I'm going to take my submanifold, and now I'm going to translate it any way I like, and dilate it any way I like. And if you'd like to add, also rotate it any way you like, and then compute the Gaussian. And I take the supremum of everything I could possibly get. Okay, another way to do this would be to fix the submanifold and look at all the different Gaussians where you change the center and scale of the Gaussian and evaluate all those different Gaussians. So this, right, so this is a number that we call the entropy, lambda, of the submanifold. We take the supremum of this. And the reason that this is important in mean curvature flow is that this quantity is monotone under the mean curvature flow. It can only go down. So this entropy is some kind of measure of the complexity of the submanifold, and it sees every scale because of the way that we consider it, at all different scales. But it's very low regularity. It's really only depending on the area, some integral thing. So it only depends on the first derivatives at that scale. It never sees second derivatives. So it's much lower regularity than asking about a property of curvature or something like that. Okay, another thing is that if you take a shrinker, then the entropy is just equal to the F functional, the Gaussian area. Somehow the shrinker, the right scale for the shrinker is the one where you haven't changed anything. Okay. So what can you say about entropy? The first thing you can say is that entropy is always at least 1. And that's because if you take any smooth point in the submanifold and you dilate that up, in the limit, you get a plane through that, a hyperplane through that point. And we said the hyperplane has entropy, it has F functional 1. Since I consider all scales, I always get at least that 1. Okay, so The next thing is that if you have a shrinker, then there's a theorems of, well, basically it's Bracke's theorem, but the version proven by Brian White, which shows that there's a gap. So this is the analog of Allard's theorem for minimal submanifolds. So any shrinker other than a plane is going to have entropy strictly larger than 1. It'll be 1 plus epsilon for some epsilon greater than 0. The next thing is that so here's a really elementary question that there should be a very easy proof for. Suppose you have a closed curve in the plane. What's the least entropy you could have? Okay, so all you're doing, you have a closed curve, you integrate the Gaussian over it, and now you consider all dilations and translations of the curve and look at all those integrals. The largest value you can get, that's your entropy. Give me tell me which curve is optimal for it. It turns out it's the circle. Okay, this is something that should be able to be done by very elementary methods, but I haven't been able to find an elementary proof. The proof that I know proceeds by mean curvature flow. So if you so if you take your closed curve and you evolve it, first of all, you can assume it's simple. Because if it happened to cross itself, when you dilated about that, in the limit, you would see something like 2 lines crossing. And so each of those lines would contribute 1 to the F functional on that scale. So the entropy of something that's with a self-intersection is at least 2. So this means the curve is simple. And so next, as it evolves, if it's simple, then Grayson's theorem says that under the curve shortening flow, it stays simple. And then the theorem of Gauge and Hamilton, it stays simple and becomes convex. And then Gauge and Hamilton says it disappears at a round circle. By Huisken, the entropy only went down under that whole time. So the entropy that I started with had to be larger than the entropy of the round circle that I finished with. And so therefore the circle has the least entropy of any closed curve in the plane. And I don't know, it's a totally elementary statement. I don't know any other proof. Okay, so Toby and I, and with Brian White and Tom Ilmanen, we conjectured that the spheres minimized entropy for closed shrinkers. So we actually proved they minimized entropy for closed shrinkers. And we conjectured that they minimized entropy for any closed hypersurface in every dimension. We actually only conjectured it up to dimension 6, because once you hit dimension 7, we didn't know what would happen, basically because of regularity issues for the plateau problem there. There might be area minimizers that have different properties. So Jacob Bernstein and Lu Wang proved this conjecture up to dimension 6. A couple years after that, Jonathan Zhu proved that it was actually true in every dimension, even the high ones that we hadn't dared to conjecture it for. At this point, we also conjectured that not only is it true for hypersurfaces, it should be true also in any codimension. By the way, it is true in any codimension for curves, and that's because of this monotonicity that we talked about, and the result that I told you earlier, which says that if you have any shrinker curve in any large Euclidean space, it's actually inside a plane. So we've reduced then to the original case. Okay, but it's not, say for instance, if you have a surface in R4, the entropy should be at least that of the standard round sphere that sits in R3. But that's not known. Okay, so Toby and I proved that, in fact, for these flows, that the dimension of PD was always finite. So this is for a mean curvature flow. The exponent on D was again n, the same as you would get in Euclidean space. Now the constant in front of that was a dimensional constant times the entropy. So as the entropy gets larger, the dimension could go up. And again, this the dependence on D is sharp. The dependence on the entropy, I would really like that it wasn't sharp. I would, so it's certainly not sharp for curves, right? So for curves, it doesn't work because you don't need the entropy there because of ODEs. As it gets more complex, the ODEs don't really come in, but it doesn't increase the number of solutions. Certainly it's going to have to depend on the entropy, but if it was something like the entropy to the n-1 over n, that would match up with what you get for curves. and that it would be asymptotic to 1, but it would be a big improvement that would have applications elsewhere. So Doug, if you happen to see that, let me know. Okay, so the case, I should say, so for this theorem, when the case d equals 1, that's the original problem that we wanted. We wanted to get a bound for the codimension, and so we get that. Okay, and so this, right, so that's the second theorem. Okay, so there's, see, now I'm thinking in terms of, at some point I pick and choose. I think I just hit that point. Okay, so this also gives a bound for eigenfunctions of the drift Laplacian, or Ornstein-Uhlenbeck operator on shrinkers. By the way, you might wonder why, because if you have an L2 eigenfunction, you don't necessarily, with an exponentially growing weight, one wouldn't necessarily guess that the function grew only polynomially. Right? That doesn't follow because the weight is blowing up. If you take e to the minus x squared over 4, that would allow the function itself to grow really, really rapidly. I mean, certainly much faster than polynomial, much faster than regular exponential, and still be in L2. But this is a result that we proved that I think was, at least I found.
So these are eigenfunctions for what operator? For
this script L operator, this drift Laplace, right? So Ornstein-Uhlenbeck operator. So it's a Laplacian, and then there's the first order part, which is the gradient dot the position, tangential part of the position.
But that's not the usual Hermite operator anymore, right?
It is on Euclidean space. So
okay, in which case you know the answer immediately, but here, because of this x of t, you've got something more complicated.
Exactly. Yeah.
Okay.
And the Laplacian is also more complicated because it's on a different space. It's no Euclidean space. It's some other submanifold that has its own issues.
But it's just the Laplacian on that manifold, is it?
That's right.
Okay, thank you.
Yeah, good. Okay, so yeah, so exactly. So what, and of course, this fact that the eigenfunctions grow polynomially with degree twice the eigenvalue, that's of course familiar for the Hermite polynomials. But in fact, we showed that this is true on any shrinker for the eigenvalues of that drift Laplacian, or right in that problem. Right. Okay, and yeah, there are a number of things there. So even this thing of getting pointwise bounds like this, these submanifolds, they don't have bounds for Ricci curvature. So you don't necessarily expect to have a good mean value inequality in that sense. Right. Okay, so anyway, I'll say more about that later. One of the things that I won't talk about, but that we're really interested in right now is within the last few days, we've proved a version of this on Ricci flows. So interested to see where that leads. Okay, so I think, let me just, I'm hitting the witching hour. So let me just say that a couple of things here. Rigidity for cylinders. Let me just, okay, so, right. All right, let me state one last theorem. So we show that if you have one tangent flow at minus infinity as a cylinder, then the flow is actually a flow of hypersurfaces in Euclidean space. So here, in the problems that I've been talking about so far, I wanted to get some fixed bound on the dimension of P1. Now I'm saying that the bound is just n plus 1 for the dimension of P1. So that's really, really sharp. Okay, so that sort of, that's a different sort of approach, and you need different techniques to do that, which I guess I'm not going to get to talk about. So anyway, yeah, Camilla, I don't want to overstay my welcome. Let me end it there, and let's go to questions.
Okay, thank you very much. So let me start with questions. So do I understand correctly the fact that you have so the thing which is going to be different on the cylinders is that you have, like, it splits one line, at least. And so the fact that it splits one line is actually going to tell you that the mean curvature flow has to be of codimension 1. That's the punchline. Yeah,
that's right. That's right. So what happens is, yeah. So right. So what's going on is we will know that our flow is close to a cylinder. Okay, so there's some rigidity of the eigenvalues on the cylinder. So if you look at the eigenvalues on the cylinder, there's a gap to any other eigenvalue. So you get all these guys, which are the ones, the cylindrical, and then you get the ones that are spherical harmonics on the sphere. You know, so you have the ones that are affine, and then you have the spherical harmonics on the sphere factor. But you can completely identify the spectrum and show there's a gap to anything else.
But maybe I'm getting, so your definition of cylinder, the cross section has to be a sphere.
That's right.
Okay.
Yeah.
It's not just that it splits off a line, but the cross section has to be a sphere.
That's right.
Okay, that is what was confusing me, because I thought, okay, I can take any. I mean, is this correct? If I take any mean curvature flow and I simply multiply by a line, I just get still a mean curvature flow, right?
That's right. That's right. Yeah, that's right. And so you could, if you took one that was not well behaved, it was not in codimension 1, right? Crossed it with a line, that would be a counterexample to a stronger version of the theorem that I didn't state.
Okay. Okay, I understand.
Okay. That's
so
right.
what you're saying over there is that if so it's a rigidity theorem which tells you that are you able to use this in a blow up? I guess so, right? So you should be able to say that if you're close to the cylindrical guy, the other dimensions are not going to count that much.
That's right.
They're going to be like short on those dimensions.
Yeah, that's right. And so it extends a lot of classification theorems. So there's been a big industry in terms of classifying these ancient solutions, Angan, Daskal, right? All the names I have here. And so all of they were interested in codimension 1 because that's where the techniques could apply. And we're able to show that all of their things can be extended to arbitrary codimension.
Okay. Do you get uniqueness of these cylinders once you have this rigidity theorem? If you're taking one,
we do. I mean, yeah, that's in a different paper. We are able to prove the uniqueness of these cylinders.
Okay. Other questions?
Well, I just have a very naive type of question. Because I don't know much about these things, but I've seen these pictures where you have dumbbells and you look at the flow, and of course there's a pinching phenomena that happens there, right? And if I don't have any symmetry, then I may not be able to easily identify where my pinch occurs and what it looks like near the pinch. So, I mean, are these things all understood now, or what?
No. And that's a really interesting problem. So the places where these pinches are incredibly unstable. So if you you can't predict it at all, right? That's a really interesting problem. And I think one of the most interesting questions is, so there's a conjecture that if you start with something like this, let's say you could either say generic or with only finitely many exceptions. As you do the flow, you only get isolated singularities. So these pinches just occur at isolated places. So in that's
a theorem, or
that's a conjecture. So with this Merry, we got a whole circle of singularities.
Yeah.
If you do, of course, if you have this with a dumbbell where the thin neck that's long, then it'll just at that one point where it's the thinnest because of the symmetries. But if you suppose
I don't have any symmetry, then I have to figure it out implicitly, right?
Exactly. Exactly. And there's no way it's so unstable, you can't track where these things happen.
You can't track it?
You cannot track it. It can jump. So we could have one where I could make an arbitrarily small, where a pinch occurs like that.
Yeah.
And you give me a number, I'll make a perturbation of the initial data smaller than that number. And yet, and a larger number, and say, then within some fixed time, no singularity at all will occur inside a ball of radius 1. I can move the singularity arbitrarily far away with the tiniest perturbation.
Oh, see.
Okay. And so this would be, what I'm thinking right here would be, say, don't just give me a dumbbell, give me an infinite cylinder, adjust it a little bit, say, so you have a singularity. I can make the tiniest perturbation, and that singularity doesn't occur here. Instead, it occurs way off over there.
And you could have many pinches in such a thing, I can imagine.
Yeah, that's right. Exactly.
Yeah.
Incredibly unstable. And that's one of the real difficulties. And it also means that we have a lot of trouble tracking what happens past a singularity, because, it's just wildly unstable. I think there needs to Yeah.
Do these techniques that Sethian uses, are they useful numerically or are they useful actually?
Yep. So Osher and Sethian, this level set method, that allows you a way to do this, and that right. So Chen, Giga, Goto, and Evan Spruck, use the theory of viscosity solutions to take that level set method proposed by Osher and Sethian and turn it into a big existence theory for the flows.
So, but they still can't say, what can they say then about this, let's say a perturbed cylinder, long perturbed cylinder, then what can they say?
They can give you that a weak solution exists, and they can give you some regularity of it, but they can't tell you hardly anything about where the singularities occur, and not that much about what it looks like.
What the structure of the singularities is at the onset of the pinch.
Yeah, that's right.
Of course, the pinches could occur at different times, right? I mean,
yes, that's right. And there are lots of conjectures there. So some of the yep.
But I think I think in that approach, like you have your flow, which is embedded in this level set of a function, which is solving these other PDEs. So it's a little bit like saying that, okay, you know this function, but the particular solution which is giving the pinching is like going to be a level set of this function. So it's kind of it's still kind of rare to, or like, a tall order to say where that is going to happen. I don't think that numerically they can really detect.
Yeah, numerically they can. Yeah, it's hard for them to get down to that.
It's extremely, it's an extremely unlikely event in a sense.
Yeah, because it's so unstable, and exactly as Camilo says, unlikely. The space of solutions where it would happen would have very high codimension. So it's like trying to find a really high index critical point.
mm-hmm.
If you were to do it numerically by Newton's method with probability 1, you're going to miss that critical point because the set of things that go into it has very high codimension in the space of initial data.
But typically, I will see a pinch, won't I?
You will typically see a pinch.
Yeah.
Yeah, you will typically see a pinch, but then locating exactly where that pinch
Well,
is.
no, locating it could be. I mean, I'm familiar with other things where you have a lot of instability that way, but yeah.
You'll see a pinch, but it may not be the right one.
But then suppose there's a pinch, then do you know that it has a nice cylindrical type singularity or conical singularity?
You don't.
Okay.
There are settings where you do. So for instance, if you have bounds on the entropy, or if you have bounds on the genus, or if you're going to perturb it a little bit, or if you know the initial data is mean convex, meaning the flow is monotone,
then you can say.
Right? But in full generality, no, you cannot. And in fact, it's very hard to, very hard to. So the regularity theory in full generality is extremely unsatisfying. So unless you make some assumption like mean convex, the best you can say is that the flow is smooth almost everywhere at almost every time, which is, it's like this statement 0.
Thank you.
And actually, even for that statement, don't you have the problem of multiplicity?
Yeah, you do. You do.
Right? This is under the assumption that you have multiplicity, that multiplicity is not kicking in. Otherwise, you wouldn't even know that, right?
That's right.
Okay, so other questions?
Yeah, I have a question. The codimension bound in terms of the entropy. Do you envision applications outside of a case where you could use this to show that the codimension is 1? Like if you somehow if you know that the codimension is small but not 1, any sort of like classification or simplification that happens there?
That I don't know. In terms of this thing with the dependence on the entropy, that I can imagine an application for, and that has to do with trying to control the generic singularities. So, because you can use very arguments from the stability argument, stability inequality type arguments. If you know something is stable or generic, that allows you to get some kind of bounds on the entropy. And then once you have bounds on the entropy, then you can plug it in here and get bounds on the codimension. And if you try to combine these things, then it comes down to how the two things depend on each other. If you want to get an estimate in the end, you need to absorb something. So you need a good constant on one if you have any hope to absorb it in the other. Right. So yeah. So if we could improve that entropy bound, then we could say. So right now, one of the results that one of the slides I skipped is we gave an entropy bound for surfaces. So stable generic surfaces in any codimension. But the reason it's stuck at surfaces is because I can't handle other entropy terms that I would be able to handle in higher dimensions if I had that better dependence.
I see. I see. Thanks.
Okay. Well, there does not seem to be other questions. Thank you very much, Bill, for the entertaining talk. And a nice evening to everybody.